So we are just on the first part of the set of slides for the topic, the first topic for midterm, and that is distillation. So I'd like to begin this slide with an overview of a very relatable practical application of distillation, and that is in petroleum refining, and how distillation as the first part of the many processes that the crude material that has to undergo plays a very important role in separating the components of the main material that is very crude, as I have mentioned in form. So hopefully you get to hear the narration, the narrative together with the video. Is the video stalled, class?
Nag-stop miss ang video.
Let me start again. I will just start again. I don't know why it stopped. Please wait. Okay, so that's it. So that's the essence of distillation. So it's the starting point in the production of several materials, or even the materials coming from the distilling column are being used as raw materials in other production processes. Now, distillation in this part actually utilizes the vapor and the liquid phases that essentially are at the same temperature and pressure for the coexisting phases or zones. So in the process of distillation, we are having in our distilling column what we call two zones, which you will later on know as we go along in the slide. Now, the process of distillation also uses, just like in gas absorption and stripping, these random or structured packing materials. If your column is not one that is using the structured or random packings, your column can be either made of plates or trays that can, as I've said, make sure that the two phases, just like in gas absorption and stripping, made into intimate contact, and that separation of a particular component, that is the less volatile component in the case of distillation, is achieved. Now, our process, distillation, may be operated continuously or in batch mode, now depending on a number of factors. So these factors are as follows. So we have to consider the scaling, the degree of the formation of the scale inside the column, the flexibility of operation. Is our distilling column going to be used only by one particular feed material, or has it to be used by different feed material? And the solid contents of the feed. So these three are very important. That way we can decide whether a column is to be operated in continuous or batch mode. Now, all the components that are present in our original feed mixture is present in both phases. So we will talk about the phases present in distillation later on. And these components are present in both of the phases. Now, vapor phase, so it's mentioned already here, one of the phases is created from the liquid phase by vaporization. So actually, in the process of distillation, we have a single feed material, unlike in the case of gas absorption and stripping, where initially the column really receives a vapor phase and a liquid phase. In the case of distillation, we only have one feed stream that is introduced into the column. And from that same feed stream, we produce the vapor phase that is going to flow counter current to the liquid that is going downwards. So it follows that our vapor phase is flowing upwards. So the two phases are contacted in countercurrent fashion. But nonetheless, the two phases here, the liquid and the vapor phases, is to contain all the components that are present in the original feed that was processed by the column. Now, in our case, to make things less challenging, we will limit the feed material that we're going to process into a two-component feed mixture. So we won't have a feed here which will have more than two components. So normally the problems that you are used to study, that is given to you to read, study, and even tackle are only composed of two components in the feed. Now, in here, so the feed material, which is to be separated into fractions in the sense that the materials that are present in our original feed have the same, or rather the components that are present have different volatility. So they are separated into fraction using this difference in volatilities. It is introduced at one or more points along the column shell. So in our problems here, we will only have one feed material that is to be introduced into our still. Though in the industry, there are really distilling columns that have more than one feed stream into one still. In your case, you'll only be tackling problems where you only have one feed stream. Now, the liquid runs down the column, cascading from tray to tray or stage to stage, while the vapor flows up the column, contacting the liquid at each tray. Now, liquid reaching the bottom of the column is partially vaporized, meaning only a portion of the vapor that is flowing down the column is turned into vapor,
And it is done by what we call as the reboiler. So it is an auxiliary equipment that has the goal of providing the boiled up vapor, or the vapor now that is going to flow countercurrent to the liquid that is flowing down. So take note, the purpose of the reboiler, it's not part of your still, it's outside of your still, it's an auxiliary equipment, is to provide the vapor. So initially, we don't have the vapor that is flowing countercurrent to the liquid feed that is going down. Now, the remainder of the bottom liquid is withdrawn as what we call as the bottoms, simply the bottoms or the bottoms product. Now, the vapor, on the other hand, reaching the top of the column is being cooled and condensed to liquid in the overhead condenser. So in your skill now, so far, you have learned that you have two auxiliary equipments. You have the reboiler at the bottom and you have the condenser on top. So the condenser, from the term itself of the equipment, it is used to turn the vapor into liquid, meaning condense the vapor into liquid. Now, what happens to the vapor that was condensed into liquid at the top of the column? So some of the liquid that was formed or condensed from the vapor is returned back into the column in the form of reflux. So the main purpose of reflux, if you're going to read from McCabe, I think it was from McCabe that I have read it, is to improve the quality of the final product, the final distillate product that is to be withdrawn in your column. That's the main objective of the reflux. Now, the purpose in here that is stated in the slide though is to provide liquid overflow. Meaning, aside from the liquid feed that goes down into your column to be partially boiled up as vapor, you have an additional liquid that goes down as well from the condensed vapor. So the purpose, again, as I've said, is to improve the quality of your distillate, the final product. Now, the remainder of the overhead stream is withdrawn as distillate or the overhead product or the final product of the distillation process. Now, the lighter, lower boiling point temperature components tend to concentrate in the vapor phase. So we expect that those that have lesser boiling points will be the one that will condense first, while the heavier, higher boiling temperature components concentrate in the liquid phase. So the composition of the vapor in equilibrium with the liquid at the boiling point of the liquid should be different from that of the liquid. And the vapor phase become richer in light components as it passes up the column, and the liquid phase becomes richer in heavier component as it cascades downwards. So it is expected, as we have seen in the video also, that the heavier components tend to settle at the bottom of the still, whereas the lighter components are the ones that are being removed or fractionally removed from the top of the column after it has undergone condensation. Now, the overall separation achieved between the distillate in this sense and the bottoms for our distilling column depends primarily on the following factors. So we have to look into the relative volatilities of the components, the number of contacting trays in each column or section. So again, you have to take note that in here, aside from you having two phases, you have now what we call sections in your still. Then we have also the ratio. So the third one is the ratio of the liquid phase flow rate to the vapor phase flow rate in each of your sections. So this time, you are to know that your distilling column has two sections. And the sections are mentioned here on the last bullet in this slide. So the column is divided into an upper section, which is often called the rectifying section, otherwise known also as the enriching section, and the lower section, which is referred to as the stripping section. So your column, again, has two sections, the rectifying or enriching section and the stripping section. Now, when we do graphical, partly graphical uh, interpretation of the given and the problem, and partly graphical procedure in solving distillation problems, you are going to use this equilibrium diagram. I have shown this to you at the start of the course in the topic of phase equilibria. So equilibrium between phases or between components in your mixture can be represented in the form of graphs. And in this case, what you have in the graph is the relationship between the mole fraction in the liquid phase and mole fraction in the vapor phase. So for a particular system, when this two is plotted, referring to XA and YA, you will be forming this curve. Okay. Now, if the problem does not give a curve for a particular system, it is us who plot the curve. So this is your XA versus YA. And then the 45-degree line is simply drawn by us as well. So what is just given by the problem, if the equilibrium diagram is not provided, is just a form of a table that has the relationship between XA and YA. Now, in this same graph later on, you are to write the 3 operating lines, or this is where the operating lines that will represent the different, shall I say, separation of the component from the liquid phase to the vapor phase happens. Okay. Now, however, if you're not going to talk about those operating lines for now, if we're simply going to look into the importance of having the equilibrium curve here and the 45-degree line, the distance between these two tells you of how easy it would be to separate the components of your given, let's say, mixture, feed mixture. So the greater the distance between this 45-degree line and this curve or line, if this is a line, the ease in the separation of the components in your original feed, meaning it's easier to separate components if the distance between these two is big. However, the nearer the curve to the 45-degree line, the more difficult it is, or we will be needing a taller column for us to be able to separate the components. The essence of that, or a graphical, let's say, illustration that would make you easily understand that particular thing of the ease and separation will be shown when we do the graphical approach later on. Now, this was also mentioned in phase equilibria, the concept of relative volatility. So in the case of distillation, if we have a relative volatility which is greater than 1, then we expect that there is separation. If it's less than 1, there won't be any separation at all that will happen. So this relationship between pure vapor pressures and concentration in the liquid phase and vapor phase equation was already presented to you in the phase equilibria process. So in terms of distillation, for us to be able to separate the components in the original feed mixture, alpha has to be greater than 1. Now, alpha varies with concentration, but for binary mixtures, and that's the most, these are the cases that we'll be dealing here. Binary mixtures obey Rayleigh's law. The variation is negligible. So for binary mixtures that are ideal, and in our case here, it's always benzene toluene, so the system is ideal. The variation in the value of alpha over a wide range of values for, shall I say, concentration that is stated here, the variation is more or less less. So though it is dependent on the changes in concentration, the variation will not be much. So it's okay that our alpha will be in the form of a constant when provided in the problem. Now, there are 2 methods of distillation. So there are several methods, distilling methods that will be discussed to you, and they are divided into 2 groups. The first group, and that is under method 1, the vapor is produced by boiling the liquid mixture in a single stage, recovering and condensing the vapors with no liquid allowed to return to the single stage still to come into contact with the rising vapors. This means that in method 1, all of the distilling processes does not have what we call the reflux liquid because of the phrase that the boiling mixture is processed in a single stage, the vapor is recovered, and no liquid after condensation is returned or allowed to return to the still. So meaning there is no reflux. Excuse me. So in the second method, that's the opposite of the first one. There is now reflux in method 2. So same as above, but part of the condensate is returned to the still and comes into contact, countercurrent, with the rising vapors through a series of stages or trays. So methods under this method 2 group are known as fractional distillation, distillation with reflux, or rectification. And by the way, these three mean the same: fractional distillation, or distillation with reflux, or rectification. And it's under method 2. The first one does not have a reflux liquid. Kindly mute yourselves, please, whoever is that. Now, in method 1, so I have indicated here the sections in your handbook where you can read some of the methods that I have here, that I have written here. Although you can read this in, if I'm not mistaken, this is also found in John Cookies, but the primary source of this slide or basis of this set of slides is now your Perry's handbook. So under method 1, we have 3. We have equilibrium or flash distillation, we have batch or differential distillation, and we have steam distillation. In these 3 cases, there's no reflux liquid. Okay? So in equilibrium or flash distillation, a liquid mixture is partially vaporized. The vapor is allowed to come to equilibrium with the liquid. Then vapor and liquid phases are separated. So this particular type of distilling process is either done continuous or by batch. Now, in the case of batch or differential distillation, the liquid is boiled slowly and the vapors are withdrawn rapidly as they form to a condenser, resulting to a vapor reaches in the more volatile component we refer to as the first portion. As vaporization proceeds, vaporized product becomes leaner in A. This means that as we allow vaporization to continue, there is less and less amount of A that is being recovered in your vapor, or that is the distillate already, the condensed vapor. Now, in the case of steam distillation, steam is used to separate components of, so take note the specific application, of a high boiling liquid solution, which by the use of steam lowers the boiling temperature of the higher boiling component. The vapors are condensed and the 2 immiscible liquid phases separated. So the one thing that is so unique about the last method here, under method 1, group 1, is steam distillation. It's using steam. So in the still itself, you have steam already inside at the bottom. So this is used only when your feed has high boiling liquid components. So that the use of the steam lowers the boiling temperature of the high boiling component, meaning you'll be able to separate, you can do separation at lesser amount of time with the use of course, added energy in the form of steam. Now, in flash or equilibrium distillation, this is how we, this is not actually the correct schema, not correct, but rather the exact schematic diagram in Gencuplis. What you have in Gencuplis is simply some form of a rectangular box, but this is how it is to be represented in a manner that is quite understandable than the simple representation of Gencuplis. So in flash distillation, you have what we call portion of the mixture which is vaporized, and then the vapor and liquid phases being separated. This was also already read a while ago. So in here, you have the preheating of your feed. You can see there is some form of a heat exchanger in which your feed is going to pass through before it's going to be processed in the still itself. Or in this case, your steel is a simple separator, which separates the vapor from the liquid. So you have a reducing valve, or we call this as a throttling valve, that reduces the pressure, enabling the vapor to be separated from the liquid in this process. So preheating of the feed and then passing the preheated mixture to a reducing valve. Now I am going to share to you a video that will illustrate in a clear manner how is this done. Uh, the, the process of flash distillation, that is. By the way, I need to read this first before you can see the video. So flash distillation is the simplest method of separation. So meaning, if you're going to compare it to the other distillation process, this is the simplest. So the feed stream is flashed into a chamber or flash drum, and the liquid and vapor are allowed to separate under equilibrium. It is flashed by throttling the feed stream to a nozzle or valve into the chamber, where the pressure drops through the valve. The more volatile component will be concentrated in the vapor stream and the less volatile in the liquid stream. The system is very close to a single equilibrium stage, and separation is usually, in this case, since it's the simplest, is not very high for a single stage equilibrium process. Although a flash distilling column can be operated one unit side by side. Okay, you will learn that in the video that I'm going to show to you. Okay, so that's in the case of flash distillation. I think everything was clearly discussed by the supplier of the said flash evaporator. I think it's the same for all flash evaporator, the system that is, or the principle behind the separation. Now, if you will get cut here or disconnected, we will use the same